Hello, my name is Charles Taylor from the University of Leeds. I work in the School of Mathematics, and today I'm going to talk about the central limit theorem. It's a very important theorem. It sounds very grand, and in some ways it is grand. And what we're going to do today is really just talk about why it's important and just state the result and different applications of its use. So first of all, we're going to look very quickly at the normal distribution, just to revise our knowledge of that. And then we're going to look at the distribution of the sample mean and how we might explore that concept, and then see how the normal distribution can be used to approximate that distribution and the applications, the main really thrust of the uses of the central limit theorem. So the outline is a little bit of revision, the statement of the theorem, an application of the theorem, an approximation, and then some further uses. So the normal distribution, first topic, is used for many data sets. Many continuous type data sets have a curve which is a nice bell-shaped curve which we can successfully model with a normal distribution. We also have the case that many discrete data sets can be modeled by a normal distribution, and this occurs where you have a very fine resolution of data. So for example, exam marks, which are usually recorded to an integer from 0 to 100, if you have lots and lots of students, you very often get a nice bell-shaped curve from these values. Of course, it's not exactly normal because you don't get values like √2 occurring in exam marks. So it's not precise, but it's good enough for most purposes. And of course, there are many distributions which are not normal at all. We mustn't forget that. So a bit of notation. So if we have a random variable x, which has a mean mu, Greek letter mu, and a variance sigma squared, we write that as n mu sigma squared to denote the mean and the variance of the normal distribution. For a normal distribution, we can standardize the random variable by subtracting the mean and dividing by the standard deviation. And so if x is normal, then z, which is a transformed x, with subtract the mean, divide by the standard deviation, is also going to be normal, and the mean of that transformed random variable is 0, and the standard deviation, or the variance, is equal to 1. And so if x is a general normal distribution, then x minus mu over sigma is a standard normal distribution. And this concept of standardizing to obtain the standard normal is very important. So what's the theorem for the central limit theorem? So we have now n random variables. So x1, x2, up to xn are random variables, and we're going to require that these variables have the same distribution and they're independent. Okay, so we use a slight shorthand there. We say they're IID random variables, so independent, identically distributed IID random variables. And we can just record two facts about this distribution. First of all, we note the mean of the random variables, which we're going to use the Greek letter mu, and the variance of the random variables, which we're going to use the Greek letter sigma squared for the variance. And it's worth stressing at this point, we're not requiring these random variables to be normally distributed. We are noting the mean and the variance, and we're using the same symbols for mean and variance as we have for normal random variables, but there's no requirement that these random variables are normally distributed. They could be discrete even, and we'll see some examples later of that result. So the central limit theorem says that if we have n random variables which have the same distribution and they're independent, then a standardized value for the sample mean converges to a normal distribution. So what it says is, it's a very powerful result. It says is for large enough samples, the sample mean is normally distributed, even if the data from which the sample mean is derived is not normally distributed. So the result formally says that x bar minus mu divided by sigma over root n, that's standardized in that way, has a normal distribution, which is standard, and the convergence is for sample sizes which tend to infinity. Another way of expressing it, it says, for large sample sizes, we can approximate the distribution of the sample mean by a normal distribution with mean mu and standard deviation sigma over root n. So the standard deviation and the mean of the sample mean, of course, are well-known results, but the fact that the x bar is normal for large N is what the central limit theorem is all about. And it's actually a very complicated theorem to prove. It's beyond the scope of this lecture, certainly, and it's not something you'd encounter until maybe the second year at university in many cases. But let's just focus for a moment on the sample mean and think, what do we mean about the distribution of the sample mean? Well, let's take a very simple toy example. Suppose we have just three values, 1, 2, and 4. And we're going to sample from this population, if you like, 1, 2, and 4, with samples of size 2 with replacement. Okay, so first of all, we're going to suppose these values are equally likely. 1, 2, and 4 all occur with equal probability. And so we could just note the expected value, which is simply a third, it's the probability of a 1, times 1, plus a third times probability of 2, plus a third, times the value 4. So the expected value we'd get as 7 over 3. And the expected value of x squared, we could note, is, in the same calculation, 1 squared plus 2 squared plus 4 squared. Each of those times a third gives us 21 over 3, so that's 7. And so the variance, which is the expected value of x squared minus the mean squared, is 7 minus 7/3 squared, which is then going to be 14 over 9. So we've computed the mean and the variance of this random variable, which has the values 1, 2, and 4 in its sample space, each with equal probability. Okay, so this random variable has a mean and a variance, but clearly it's not normal. Okay, 1, 2, and 4 are a population or a sample space. It's not even continuous. Okay, and we can note the standard deviation, if we wanted to, is just the square root of the variance. Okay, so remember, at the beginning here, we're just going to write down again the mean and the variance. And now we're going to look at the sample mean. Okay, so the sample mean, remember, we're taking samples of size 2 from this population. Now, a sample of size 2 from a population which has only three possible values, we can actually enumerate every possible sample. And so if we imagine the first draw could be a 1, a 2, or a 4, and the second draw could be a 1, a 2, or a 4. And for each pair, we could write down the sample as an ordered pair. So in this table here, it shows the samples. 1, 1 says the first element was a 1, the second element was a 1, 1, 2, first element a 1, second element a 2, and so on. We can actually write down this very simple example, every possible sample that we could draw from the population. And then for every possible sample, we could also note the sample mean. So the average of 1 and 1 is just 1. The average of 1 and 2 is 1.5, and so on. So we have a list of samples and a list of sample means. And so corresponding to those sample means, we could write down the probability, the distribution of the sample mean. So the possible values the sample mean can take: 1, 1.5, 2, 2.5, 3, and 4. And for each of those, using the table at the above, we can see how many times they occur out of the 9 possibilities. And those gives us the probability of that sample mean occurring in a sample size of 2. And so that table there describes precisely the distribution of the random variable capital X bar, where the sample size is 2. And so that, if you like, is the sampling distribution, or the distribution of the sample mean. And it's this quantity here, this X bar, that we're actually interested in exploring in the context of the central limit theorem. And so we might say, well, here's a sample of size 2. This is clearly not n going to infinity. This is n2. It's not big at all. And it's obvious here also that we don't have a normal distribution. Okay, this is no way we could think of this final result as a normal distribution. It's still discrete, it's very lumpy, and it doesn't have the right shape. What we could do, just for the time being, is to check that the expected value of the sample mean random variable is the same as the random variable itself. So the expected value of x bar is the same as the expected value of x. And again, we can just do that by looking at the sample space of x bar. So it takes values 1, 1.5, 2, 2.5, 3, and 4. Each of those has an associated probability, and so we can compute the expected value in the usual way from the formula just by looking at the distribution. And similarly, we haven't written down the calculations here, we could do the variance by first of all getting the expected value of x bar squared, and we would find, having done that, that we get the result sigma squared over n. So it's an exact result for the expected value and the variance, the expected value of x bar being mu, and the variance of x bar being sigma squared over n. That will always hold, but the central limit theorem says more. It says the distribution of those quantities tends to a normal. So it's not just a statement about the expected value and the variance, it's a statement about the distribution. But I thought this would be helpful just to see what we mean by a distribution of a sample mean. And then we can look and see, well, what happens as we increase n? Okay, so the next stage, if you like, in this toy example is to say, let's increase the sample size. Rather than having sample size 2, let's imagine larger values. Now, of course, we can write down, as we did before, every possible case for sample sizes 2. We'd have to be very patient to write down every possible case when we have sample sizes of 10 or 20 or 100. And so at this stage, what we might suggest as a way forward to explore this is to try a simulation. So say here again, I'm not proving a central limit theorem, I'm just demonstrating it. And so what I'm going to demonstrate here is for the same example, where we have possible values 1, 2, and 4, we're going to simulate lots and lots of samples, and for each sample we're going to compute the mean and the variance. And we're going to draw a histogram. Okay, so this picture here, which we have 3 different cases, the left-hand one shows a sample size of 4. Okay, so it's a bit bigger than 2. And what we have in the histogram, which I've scaled to a density, is over the 1,000 samples of size 4. I'm just showing how many of those are in each range. And you can see the distribution is still very discrete. Okay, it's got big gaps in it. We haven't got values in certain ranges because they're just not possible. But you can also see a tendency towards a normal distribution. So although it's very spiky and bumpy, I've drawn the normal distribution behind just to show what we're sort of converging towards. So if n equals 4, it really isn't very good. And the result is for n going to infinity, so we wouldn't expect n equals 4 to be much good. The middle picture, we have sample sizes of 10. So we have 1,000 samples of size 10, and again we're drawing the histogram of the sample means, as it states there. And in each case of the 3 pictures, I've written down the sample mean and the sample standard deviation of the 1,000 sample means. That sounds a bit convoluted. So it's a mean of means and a variance of means, or a standard deviation of means. And you can see from the 3 pictures that the mean value at around about 2.25, 2.3, 2.33 is very close to the population, or the expected value of x, which was 2 1/3. And you'll notice that the standard deviations of the sample means are decreasing as we'd expect. So on the left we have 0.616, in the middle 0.389, and on the right 0.127. So you can see for n equals 10, we have a distribution which is now looking very normal, and n equals 100, we're pretty much there. We're always going to expect some variation, because it's a simulation, but for sample size 100, we certainly have got there.